Let's talk about a tool you probably use every single day, the URL shortener. On the surface, it seems so simple, but underneath, there's a ton of fascinating engineering going on. So let's dive into the surprising complexity behind these tiny links.
I mean, think about it. You take a huge, messy web address. You paste it in, and like magic, out pops this perfect, tiny, shareable link. So have you ever stopped to wonder what's really happening in that moment? How does it actually work?
And this right here is the whole reason they exist. On one side, you've got this absolute monster of a URL. It's long, it's filled with tracking junk, you could never remember it, and it looks awful when you share it. And on the other side, something clean, simple, and elegant. So at its heart, the idea is actually super simple. The best way to think about a URL shortener is like a giant digital address book. All it's doing is taking that long, complicated address and giving it a short, easy nickname that points right back to the original. Okay, so here's the basic flow, step by step. First, you give it the long URL. The service then cooks up a unique shortcode for it. It saves that connection, shortcode points to long URL, in a database. Then it gives you back your brand new short link. And of course, when someone clicks that link, the service just looks up the original address and forwards them right along. Sounds easy, right? Well, this is where it gets interesting. The devil is always in the details. All right, so the first big engineering hurdle we hit is how do you actually create that shortcode? I mean, this is kind of the secret sauce, right? It has to be unique for every single link, it has to be generated super fast, and it needs to work at a massive scale. So, engineers basically have three main playbooks for this. The first approach is just a simple counter, 1, 2, 3, and so on. The problem? It's predictable. And if you have servers all over the world, they can't all be asking what's the next number without creating a huge traffic jam. The second method is using a hash, which makes sure the same long URL will always get the same short URL. And the third way, which a lot of modern services use, is just to generate a random code and quickly check if it's already been taken. Each of these methods has its own trade-offs. Now, no matter how you generate the code, it's almost always represented in something called base 62. Think of it as the alphabet of short links. It's just A to Z, both uppercase and lowercase, plus the numbers 0 through 9. And why this specific set? Well, two big reasons. One, it lets you pack a ton of possibilities into a very short space. And two, every single one of those characters is perfectly safe to use in a URL. No weird symbols that might break things. And if you want to know why that matters, just look at this number. We're talking about over 56 billion unique combinations, and that's with just 6 little characters. That is the power of base 62. It's how you get a system that can handle a nearly infinite number of links while keeping them all incredibly short. Okay, so we've got our shortcode, but creating the link is honestly the easy part. The real challenge? When millions of people around the world are clicking on these things every single second, you need that redirection to be instantaneous. And just looking it up in a database every time, that's just not going to cut it. It's way too slow. And here's the key insight. The whole system is what we call read-heavy. Just think about it. For every single link that gets created, that's a write, it might get clicked on or read thousands, maybe millions of times. So something like 99% of the system's job is just looking up links. And that tells the engineers exactly where they need to focus their energy to make things fast. And the answer, the absolute game changer, is caching. It's a simple idea. You just store the most popular, most clicked-on links in a special, super fast chunk of memory. That way, you don't have to go all the way back to the slow database for every single click. And honestly, getting that cache hit rate above 90%, that is what makes or breaks the performance of the entire service. And this chart right here shows you exactly why that's so critical. A normal database lookup could take, say, 20 to 50 milliseconds, which doesn't sound like much, right? But a hit from the cache? We're talking 1 to 5 milliseconds. It's a night and day difference. And when you multiply that tiny little time saving by millions of clicks, it's everything. It's the reason the whole system feels instant. All right, so our system is fast. Awesome. But now for the next level. How do you make this thing work reliably for literally billions of people scattered all over the planet? This is where we get into some really serious large-scale system architecture. Because once you go global, a whole new set of headaches pop up. Your single database starts to choke. The sheer fire hose of clicks can totally swamp your servers. And, of course, Someone in Tokyo clicking a link that's handled in New York is going to feel that delay. We call that latency. So, what are the tools in the engineer's belt for this? Well, first, they use something called a load balancer. It's like a traffic cop, spreading out all the incoming clicks across a whole fleet of servers so no single one gets buried. Then, they break up that giant database into smaller, more manageable pieces, a technique called sharding. You can think of it like splitting one giant phone book into volumes for A to M and N to Z. It's just way faster to search. And finally, they put those caches we talked about in different spots all over the world, so the data is always close to the user clicking the link.
Okay, so at this point, we've designed a system that's fast and it can scale to handle global traffic. But we're missing one last absolutely critical piece: security. We have to protect the system, and more importantly, protect its users from bad actors trying to use it for spam, scams, and phishing. And that means building up some serious defenses. The system has to be constantly checking new links against known blacklists of malicious sites. It needs to use rate limiting to stop a single spammer from creating thousands of links in a minute. And yep, it might even throw up a CAPTCHA to make sure it's a human, not a bot, creating the link.
All right, we've talked about the secret sauce for the shortcode, the absolute need for speed with caching, how to scale it all up for global traffic, and how to lock it down with security. Now we can finally put all those pieces together and see the final blueprint. And it's kind of wild to think that this all started with such a simple idea, right? A digital address book. But to make that simple idea work for everyone, everywhere, all the time, it has to grow into this incredibly complex, high-performance global system.
So what are the big takeaways here? First, that little shortcode is a much bigger deal than it looks. How you create it has huge implications. Second, for a system like this that's mostly reads, caching isn't just a nice-to-have, it's everything. And third, and maybe the biggest lesson, is that even the simplest ideas can become amazingly complex when you try to make them work for the entire world.
And that really leaves you with a final thought, doesn't it? We just pulled back the curtain on a tool we all use without a second thought and found all this incredible engineering inside. It really makes you wonder, what other simple, everyday tools are hiding that same level of complexity, just waiting to be discovered?